Hi there, I'm Christopher Worst, and this is the second video of Homework 1 in Material Energy Balance, specifically going over question 3. Question 3 asks a student to explain the relevance of the Antoine equation as it relates to the phase diagram of a pure substance, fit the experimental water vapor pressure data on our GitHub site to the Antoine equation by nonlinear regression, and transform the Antoine equation such as to enable linear regression. So, let's first pull up a pressure phase diagram, as well as write out the Antoine equation. So, the Antoine equation is the log base 10 of the pressure of a gas is equal to A minus B over C plus the temperature of said gas. So, A, B, and C are experimentally determined values that are specific to a substance. So, and on this temperature, on this phase diagram, you can see that as temperature rises, so does pressure. That is shown in the equation, as you can see for yourself, because the pressure is equal to A, which is a constant, minus B, which is a constant, divided by a constant C times T. As T rises, going this way, going to the right, so does the denominator of the fraction. And so that means that obviously overall it gets smaller, so A is being subtracted by less and less. So in total, the pressure rises as well. Now, I'm going to write on the board to explain how we're going to use subsquared error as well as linear regression via matrix multiplication to fit this in collaboratory. Start there. I'm going to explain now what subsquare error is and how we use it for nonlinear regression. So, if you bear with me, subsquare error, I'll draw a line as well as some dots here and there. We'll call this the line of best fit, so that the distance between any one of these dots, any one of these experimental values, is the error. Error here. So, subsquared error, or SSE, is the sum of all of these errors, sum of error squared, sum square error. So sum of the error squared. Or if you want to do it this way, the sum of the error, so the error being x or y, y experimental minus y not being the trend of best fit squared. So if you square that up and add it all up, and then if you minimize it and make it 0, then you have your line of best fit that fits the experimental data the best. So moving on to linear regression, we're going to start with, we're going to use matrix multiplication for this. So to start, I'm going to multiply out. I'm actually going to, not erase that, no. I'm going to leave that up there because this will be useful later. So, log base 10 of P of the pressure equals A minus B C plus T. So, let's begin with multiplying C plus T to both log 10 of P and A. Goes to log 10 of P, C plus T equals A, C plus T minus B. Next, going to move down, same thing for row movement. So we're going to get log 10 of P, C plus log 10 of P times T equals AC plus A T minus B. So for matrix multiplication, now that we have all of this out, we want to find a design matrix. So that means we have all of our, or something that we can multiply by all of our variables to get our known thing. The only number here that we know immediately based on experimental data that we'll be using later is log 10 of P times the temperature. Everything else has a variable here, two variables here, two variables here, and a variable here. So we want to move it together, move log base 10 to one side, log base 10 of temperature to one side, everything else to the other. So we can get our result matrix, design matrix, and unknown matrix here. So we're going to move AC plus AT minus B minus log 10P C equals log 10 P times T. So now, we'll look for a matrix. I'll draw a matrix. A matrix of variables, we'll call it vector V. We'll call this design matrix, or DM, equals another matrix here. We'll call this result. So, we don't know anything here, we don't know anything here, but we do know temperature in log base 10 of P. So if we were to say log base 10 of P, or sorry, negative log base 10 of P times C was equal to, sorry, I will move that to the center, because, spoiler, this is going to be a 3 by 1 matrix, C, plus T times A times, now we have these two that can't be multiplied by anything to actually create a known answer. So we're going to have AC plus minus, AC minus B, we'll make this equal to D. So now that we have all of that, we have just 1. So we're going to make this 1 times D. So this is, of course, log base 10 of P1, T1, and 1, minus log 10 of P2, T2, and 1, all the way down to minus log 10 of Pn, Tn, 1. And if we multiply all of this out, we should get log 10 of P times T, log 10 P times T, all the way down to log 10 Pn times Tn. So, we're going to do that. That is basically what we're going to do. I'm going to do that by, so if this is a, n by 3 matrix, n times 3. This is a 3 by 1 matrix, 3 by 1. And this is a 3 by 1 matrix. So, we're going to move this over to this side here for more space. So we've got dm times v equals r. So this is an n times 3, n times 3, a 3 times 1, and a 3 times 1. Now, obviously, matrix multiplication dictates that if I were to multiply these two, this would be n times 3 times 3 times times a 3 times by 1. That means that this would be an n times 1 by 1 matrix that would have n length, or n number of rows in one column. That's obviously not our result. So, instead of doing straight this, we are going to do dmt equals D, oops, let me erase this, times dmt times r. Now, dmt means the transpose of the design matrix. That means that instead of an n by 3, it is a 3 by n. You simply swap the number of rows and number of columns. So that turns that into a n times 3, n by 3, or a 3 by n, since the transpose is first times the n by 3. This turns this into a 3 by 3 times 3 by 1 equals, now, dmt is a 3 by n. Oh, sorry, this is a not 3 by 1 and n by 1. And n by 1, correction there. So, 3 times 3, 3 times 1, n, the 3 by n times the n by 1 is a 3 by 1. That we actually can multiply using linear algebra, and especially on the computer, to have it here. 3 by 3 combined with the 3 by 1 will get you a 3 by 1 to solve for the variables. So that is all we're going to be doing. We're going to be doing SSE for the nonlinear regression as well as the matrix multiplication for the linear regression. And let's get started on that. Okay, now that we're ready to start coding, I have the collaboratory file opened up here. Homework 1, question 3. I have our raw data here. And I have the homework 1 thing. So we're going to start by fitting the experimental water vapor pressure data on our GitHub site, again, here, to the Antoine equation by nonlinear regression using sum squared error on the board. So we're going to start by using !wget. I'm going to just simply get this thing, Control V, Shift Enter, and put it into the code so we can reference it later. Now, we're going to import all the necessary libraries and things like that. So from scipy.optimize, import minimize. We also imported numpy as np just for shortness, and scipy.optimize is a library. We're also going to from plotly.io import make subplots, then import plotly.io as PO, and finally, just for our eyes, and because everyone uses it nowadays, default there equals, oops, plotly dark. That will set our, oops, I forgot an I. Shift Enter. Now, make subplots. Oh, plotly dot subplots. There. Now we've got dark mode and everything is imported. So we're going to start by turning all of the string values, all the letters, all of that into actual usable data using np.loadText. And the name of our file, watervaporpressure.csv, vaporpressure.csv, shift and oops, I forgot, delimiter equals comma. Now shift enter. Now can read the commas and say, let's skip over this. Okay, so we're going to start by creating two arrays for the temperature. T equals data, the entirety of the thing, the entirety of the first line so that is what row number and what column number. So we want the entirety here from beginning to end of the columns and then we want the first value. Enter log 10p equals data here. Again, we want the entirety of all the rows, and then 1 being the second value. Shift enter. Okay, now let's print, print t. Shift enter. Now we have the values, and then let's print log 10p. Shift enter. Now we have all those values. Good. So now that we have all of our data set up, let's start by making the individual. Let's start by making the function for the sum squared error. So define SSE, excuse me, colon to make a function. So we're going to unpack this by A, B, and C equal V. Enter. So all we want to return is, and we'll do this inside out. So the sum squared error, the sum of the errors, y minus y naught squared. So we're just going to return the value here. So it will be the entirety, and we want to make it equal to 0. So we'll put the log base 10 of p on the right side. So a minus b, parentheses b, divided by c plus t minus log 10p. So that is, and we want that equal to 0, so it shall be. So we want to square this. Squared. And we also want the sum of it. So np.sum. And this is what we want to return. So return np.sum, the square of the value. So shift enter. We have that there. So now that we have this here, we're going to minimize it. So we're going to want to return values equals minimize. What are we minimizing? SSE, and we want the input, 1, let's call it 1, and let's call it 1. Okay. And .x will return only the values for these. So A, B, C should be this, just these values. Okay. So if we print A, B, C, we have values here. That's interesting. I do not believe that those should be what they are. Let's see. Let's go back and just hit minimize. SSE 1, 1, 1. Shift enter. Optimization terminated successfully. 0, 0, 0, 1, 0, 0, 0, 1. So this is why it's not right, is because I forgot to np.log 10 data. Shift enter, try that again. Optimization terminated successfully. Now we have actual values. So if we want to make this, if we want to return just these values at the bottom, we have the array here, and we want to make this equal to A, B, and C. Shift enter. Awesome. Now if we were to print A, B, and C. Shift enter, we have our values here. So that takes care of the first part. We have fit the experimental on our data to the Anchoron equation by linear regression. Now we're going to do, sorry, not linear regression, now we're going to do linear regression. So we want to create the things here. So we want negative log 10 of p, t, and 1. So we're going to make design matrix dm equals np.c underscore, that means np.c concatenate, which will make columns, a bunch of columns, and actually form it out. And we want specifically negative log 10 p, we want t, and we want np.ones like, or sorry, underscore like t. That will make the amount of t's. Shift enter, class not callable. Aha, I forgot things here. Try that. There we go. Now if we were to print dm, shift enter, we have a bunch of our a big column here. So now all we're going to do is exactly what's written up here. We're going to multiply the transpose of dm times dm and use lineage to dm transpose times r. So we're going to np.lineage, that is the necessary formula. So we're going to have dm.t, sorry, big T, at means matrix multiplication, dm, as well as dm.t at, and to make this resulting formula here, remember that it's just log 10 of p times t. So log 10 p times t. Shift enter. Module object is not callable. Oh, I forgot to give values, assign values to it. So let's call it A2, B2, and C2 just to make sure that it's valuable. Shift enter. Oh, right, I forgot the terminology. np.lineage.solve. Now, there we go. Okay. Now, let's print A2, B2, C2. Shift enter. So, if we look at this, we have negative 36 as C as A and C. That's interesting. 10.22, we have that here as B2 instead of A, then negative 2 and here. This is interesting. Now, this might be caused by our initial design matrix. Right, so T, because of our the way we set stuff up, log 10p. Now, shift enter. And sorry, we're going to actually rename this because now that I think about it, this is D, not C2, this is D2, D. Shift enter. Oops, sorry, I need to send that. There we go. So now we have 10, negative 34. Now we have, and sorry, this is actually C2. Getting all of my variables mixed up. There we go. Now we have A2 as A, C2 is close to B. Now D, where's B? Well, D is here, and remember from our thing earlier, D is equal to A times C minus B. So D, or well, B2 equals, if you want to add over and subtract over, D minus A2 times C2. Shift enter, Let's add B2, Shift Enter. Now you see that negative 17171 is close to 1756. So we have that there. Now we can fit it on a graph just to show that it worked, as well as to minimize this. So let's make a graph. Actually, if you look at it, before I do that, negative should be positive. So let's swap these around. A2 times C2 minus D. Shift Enter, Shift Enter. Now that's positive. Now we're good. So we're going to plotly, PO dot subplots, PO dot make plots. Now we're going to make the figure, so fig equals make underscore subplots. We use the function we called up here. Enter. Fig equals PO dot add scatter. We're going to add our points. X equals t. Y equals log 10p. And we're going to make it points by doing mode equals markers, as well as, let's call it, no, let's do that, that's good for now. Shift add, plotly attribute, has no attribute, add scatter. Aha, right, sorry. So if fig is equal to make subplots as this entire thing, so fig add scatter. Better. Now we have our plots. And we're just going to name this equal to data. Shift Enter. Okay. So now we're going to make a line through it. We're actually going to make two lines through it. So fig dot add scatter. Oops. Sorry, I'll turn my phone on silent. Add scatter x equals, if we want to fit this, if x, oh gosh, there we go, sorry. If x equals t, or if x equals your, again, I'm sorry, I need to add a few things. We're going to make t naught or t0 equal to np.linspace, numpy, linear spaced. Let's call it start, stop, and how many. So let's start at 250 dot stop at, where we stop? 650 dot, and let's do num equal still 100. So if x equals t naught, then if we minimize this due to this, let's do y equals, we're going to add in the Antoine equation here, log 10 of p is equal to a. We're going to use first the SSE here, so a, b, and c. A minus b divided by c times t0. And then I'm going to do mode equals line for a line of best fit, as well as name equals, call it Antoine non-lin. Shift Enter. Now, sorry, lines. Shift Enter. There we go. Well, that ain't right. Aha. Sorry, issue with our thing here. Still have an issue. What is the issue? Aha. Well, I know where I messed up. This should be a plus. Oh, much better. Now, we're also going to add to the same plot, add scatter x equals t0. Now let's do the linear. So y equals a2 minus b2 divided by c2 plus t0. Here, we're good there. Mode equals lines, and then name equals linear. And we have that, and you can see that they are in fact, very similar, albeit slightly different. 0.903 to 0.904. So it's very similar, but slightly different because of the way we did it. But it does work. That's all there is to it.